Please stop. I don't think I you up.
Well, I was worried that Blair might have another quote put on her or something, for being on the recording. So
Claire might everyone's gonna see it.
So we're gonna try to. I have no idea how much of this we'll get through today, but we're gonna try to. Almost everything you need to know now. I think the hardest part about this is going to be that some of the graphs are going to look a little bit weird, and so what I want to just kind of encourage you to think about before we go is we have to be solid on all the stuff we've learned. We have to be solid on where the holes are, how to find the x-intercept, x-intercepts, sometimes the y-intercept, the asymptotes, like that all has to be in place. And then sometimes the construction of the graphs can get a little bit tricky. If we get through all 8, excellent. Will we? I absolutely doubt it, but we're just going to give it our best shot. So the same instructions. So there's directions up at the top of the page. This just kind of like the last time I did this. This originally started out as a homework assignment, and then I thought, nope, this doesn't make sense. Let's use this one as a togethery notesy kind of thing, and then I'll have a follow-up assignment for you probably tomorrow. So let's get to it. So the order that I wrote those things in and the directions is not relevant. It doesn't. Let's just kind of stick with whatever routine we're comfortable with. So for number 1, let's get started. Like, what do we do first?
Factor?
Yeah, I mean, that's just a non-negotiable. Thank you for saying that. So factoring is critical. What is the top of this one going to factor into? Yeah, perfect. So our top is 2 times x minus 1. And then what's our bottom going to factor into?
X times x minus 3.
Yes, x times x minus 3. You guys good? Oh, it's not very nice. So let's get started. What generally has been our flow? What was it's been a few days. What was the first thing we generally was it horizontal? So let's talk about horizontal asymptote. Does it have one?
Yeah.
It is at 0. Good memory. Very good. So remember, when there's the degree on top is 1, that means there's only x to the 1th, and the bottom is x to the 2. When the bottom has more x powers than the top, then there's a horizontal asymptote at 0. So we're just going to write that down. So HA at y equals 0. Next in our list of things to do was to find a vertical asymptote. Does this have a vertical asymptote? Okay. I agree, but there's another one too. And this is where the newness starts. And about, I think, half-ish of these problems are going to have this, but there's no law that says there can only be one. It has to be 0. We have to ask ourselves the question, and we've done this before in different contexts over time, but like we have to ask ourselves what makes the bottom equal 0. And yeah, I agree that 3, if you put it in the parentheses, makes a 0, but don't overlook the fact that right here, I'll circle it for you, there's another lonely factor, and that factor can also be made to equal 0. And so there's going to be another vertical asymptote at x equals 0. You can have multiple vertical asymptotes. It's okay. You cannot have multiple horizontal asymptotes, not with functions, but verticals, you can have several. What's after that? X-intercept. And how do we find an x-intercept? Make the top equal 0. And so the top is the 2 times x minus 1. What could make that equal 0? 1. So we know that the x-intercept will be at 1, 0. It's actually a relatively pleasant problem just in the sense that nothing canceled out. So there's no confusion between like function and reduced function, like post-reduction function or post-reduction, I think I called it. How about a y-intercept?
Probably x is 0.
Okay. So where's it going to be?
None.
There isn't.
Good for you guys. That was quick and impressive on a Monday, not quite morning, but still impressive. Listen, we talked about, I think I used the term, I just make stuff up as I go, but I think I said hot lava was what I was saying. And the moment you say there's a vertical asymptote at x equals 0, you've established now that the y-axis is completely off limits. Nothing can touch the y-axis. And so by definition, a y-intercept cannot exist. And you could prove that by putting 0 into the function and seeing the bottom of it go to 0, or you could just reason your way that the y-axis is now hot lava, but the y-intercept there is none. The graph never crosses the y-axis, never touches the y-axis. And the last thing would be a hole. And again, I would say none. Why? Because there were no factors, algebraic factors that canceled from the top and the bottom. So I think we have everything now that we need. If you don't have a ruler, make sure that you get one, unless you're not worried about how things look. But it's time to sketch some asymptotes. So I cannot, I mean, I'll never stop stressing this, but I can't stress enough. Building the skeletal structure of the graph is beyond critical. And the asymptotes are what build the skeletal structure. So I'm going to start with my vertical asymptotes. There are 2 of them. There's one of them at x equals 3. So I'm going to go to 3 on the x-axis and draw a red line. If you notice, if you've looked at any of my answer keys, you know that I like to draw those dotted, but it's really annoying to do with a tab. So I'm just going to leave them solid for now with this particular writing tool that I'm using. And there's another vertical asymptote at x equals 0. So I'm going to grab in another, bless you, another red line here. And there is also a horizontal asymptote at y equals 0, which is going to be here. So we understand that the red lines are not quote unquote part of the graph, but their existence is essential in that they guide us as to how things are going to bend and mold and fit. How many regions have we created? 6. I see 6. There are 3 above the horizontal asymptote, and there are 3 below the horizontal asymptote. This is our first time seeing a rational function like this. And so I want to just go through and sketch for you some of the different things that can happen. Don't write anything down that you're about to see me write down. It won't end well, but here's a possibility. A graph could go like this. Okay, that's a possibility. A graph could also go like this. And honestly, I don't know if I want to waste your time with showing you all of the possibilities. There are lots and lots of things that this graph can do. But what we really want to do to be expert at this is we want to understand that the vertical asymptotes are really the regions that we want to focus on. We know, based on the definition of the word function, that a function has only one output for every input. So we know that the graph cannot look like this, correct? Like if Layla has gone to the left of this vertical asymptote and has selected an x value like -1, and she has found a y value to go with it, then she has determined where that arm of the graph is going to be. It can't exist above and below itself, which is why we use the vertical asymptotes to separate into regions. And then we simply test the regions and we start to piece together the puzzle of what the graph looks like. That is the only respectfully decent way, I think, to teach how to graph a rational function is just good old-fashioned roll up your sleeves.
They can't share an x coordinate, but could they share a y coordinate?
Of course, yes. There's lots of times where we see functions that have, like this. We've seen this before, right? Yeah. As long as you're not above or below yourself, but you can't be above. So let's get to it. Let's try to piece together the puzzle, and let's begin with a number, any number you pick, that is to the right over here. So say again. 4 is absolutely gorgeous. 4 is right here on the x-axis. And if I pick 4, then I can put it into the function and I can do some like 6th grade math and simplify it down, and it'll give me a y value. And the what's so important about that y value is it tells us, is this arm of the graph going to be up in the quadrant 1-y kind of place, or is it going to be down below in that quadrant 4 kind of place? So let's just work it out. When you calculators or no calculators, I don't really care. But if you put 4 where all of these x's are, you just have to math. So it looks to me like 4 minus 1 is 3, 2 times 3 is 6. And then I'm just going to do the math, okay? Just not that I don't trust you. And then if I put 4 in the bottom, that's 4 times 4 minus 3 is 1, and that is indeed 6/4, which I'll reduce to 1.5. Everybody okay with that? So we just established that at the input value of 4, there's an output value of 1.5. And that is critical because it now tells us where that curvy arm. The outside arms of these rational functions are going to predictably be those boomerang shaped things. The middle is the complex one where we have to do a little bit more investigative work. But once we know that 4, 1.5 is a point, I'll put it right here in purple. Then we now know what that side of the graph looks like. If you wanted more evidence, there's nothing stopping you from putting more numbers in. Like just if you wanted to verify, put in like 6. And again, just do the little kitty math, like up on top. 6 minus 1 is 5. 2 times 5 is 10. And then on the bottom, 6 times 6 minus 3 is 3. 6 times 3 is 18. And 10 18ths reduces to 5 ninths. And sure enough, right on cue. That means if I go right to 6, I'm just a little bit above halfway to 1. And predictably, the graph is doing exactly what we would have suspected it's going to do. Except I didn't go far enough to the right. Apologies for that. So go to 6, not 5, dingus. There you go. So do we know what that arm does? Like we can sketch it now, right? And apologies in advance for this sketch, but just do the best we can here. It's that bottom one that always gets me. You can't make judgment calls. I mean, someone who does this all day, like I don't know, like someone who does this sort of like graphing analysis like for a living would probably know. But in my experience, like I can't say that the other arm of the graph is going to be up here, and I can't say it's going to be down here. I'm just going to give you the same speech again. You got to figure it out. So what's a good number to the left of the leftmost vertical asymptote? -1 seems a logical choice. So we're going to take -1 and we're going to plug it in up there where those purple arrows are pointing. And again, we just have to do basic math. -1 minus 1 is -2. 2 -2's make -4. And then on the bottom, we have -1 times -4, which is 4. And I believe that's -1. Is that correct?
That's what I got.
So at -1, we get an output of -1. And so now we know, like that graph isn't going to, these outer arms of the rational functions are very predictable. So if you know a little bit, but again, if you want to validate and do more, you can. But if you know a little bit of it, you can fill in the dots and do the rest of it. So if you wanted to go check like -2 and -3, you are welcome to do that. But the graph is going to do this. And that is a really ghetto sketch, but that'll do. And now the part of this lesson that I wasn't looking forward to. The first thing I want to say is this. Graphs can cross horizontal asymptotes. Horizontal asymptotes are not hot lava. They're limits. They're what graphs tend towards, but that doesn't mean that they are unable to touch them or cross them. So there are 3 things that will now happen. One of 3. Well, one of 4. Here they are. Option 1. The graph might be parabolic in the center. Option 2, it might be upside down parabolic in the center. And then the ones that are really confusing they could be like this. The center can actually behave like that, and it can also do the backwards of that. So this is where you're going to find yourself spending the most time, is asking the question of what is it doing in the middle? And to do that, we just need to roll up our sleeves and try numbers, do math. 1 point in the middle, I don't think is going to be enough. Does this graph have an x-intercept? It does. Maybe that'll be some useful knowledge for us here. Why don't we go ahead and take that and graph it? I'll put a nice big green dot right where the x-intercept is. That's useful knowledge. So the graph will touch or cross the x-axis right where that green dot is at. That might come in handy. So let's get in there and let's find some more x values in the center so that we can piece the puzzle together. So what's another x value that's in between, sandwiched in between the vertical asymptotes? 2. And if this isn't enough information, then we'll have to do fractions, and our calculators will help us a lot. We'll just do decimals and plug them in. So let's do 2. Again, let's work it out. Just do the math. I got -1. Anybody else get that? Input of 2, output of -1. Does anyone want to take a guess as to what the graph currently does? It's a snaky. Good. It's like a cubic. We've seen these before, but let's just verify. Let's make sure that what we think is going to happen is going to happen. And to do that, let's take something like 0.5. And this is where having a calculator out and handy would be pretty helpful, pretty useful. So if you take 0.5 and put it in the top, that's 0.5 is -5. I believe the top comes out to -1. And then 5 minus 3 is -2. It comes out positive, and that's pretty useful. It comes out to roughly +1, but not quite. It's a little bit below +1, which means, and let me zoom in on this so you can really see up tight and close. That means that if I put in 1/2 for my X, I get out. Did anyone actually calculate what it is? It should be like 0.8 or something like that.
You said fraction of -1.
That's what I did too. So I get whatever that is, it's going to come out to be right about here. 4/5. Perfect. And there you go. And so we can now get up nice and close and personal and actually see the behavior of the graph. If you wanted more evidence, you could take another X point that's further left than that and do like 0.25 or 0.1 or something like that. And you could even go further to the right of 2 and do like 2.5. But we know enough now to say, I know what the graph's going to do. And the graph is going to be a snaky, and it's going to go like this. Question. So let's take a quick moment to make sure that we followed all the directions and that we have all of the characteristics intact.
Did it go all the way off the graph, or are you okay if we do like that?
The way I have it is fine just because I have my arrows. So as long as you've got the arrows to indicate that it keeps going. Sometimes when you have that much real estate to work with, you kind of draw it for a couple inches and then you're like, I'm over it, you know? You don't want to keep going. I get it. Because it's almost like you're graphing basically vertically at a certain point. So no holes. We got both our asymptotes vertically. We got our horizontal. Our x-intercept is fine. And why is there no y-intercept again? Because there's a vertical asymptote right there. So 1 down, 7 to go. Make sense? Okay, let's do number 2. Same order of operations. Let's start with horizontal. Oh, let's factor first, I guess. So if we pull a 2 out of the top, it's 2 times x squared minus 5x plus 4. What does that factor into?
-4x minus 4 times x minus 1.
Yeah, so 2 times x minus 4 times x minus 1. And then the bottom is some pretty old school, like algebra 1 factoring. What's that going to be?
X minus 4 times x minus 3.
Yeah. So there it is, all of its mathematical DNA out exposed, and now it's time to go through our list, our to-dos. By the way, there will be none of these on today's. I'm not going to do slant asymptotes with you guys for a while. When a graph doesn't have a horizontal asymptote, it probably will have a slant, and we're not going to go there. So all of them on this note thing in your homework are going to either have degrees matching or degrees small on top, big on bottom. Just FYI. On purpose. So where's the horizontal at? Nice. Absolutely perfect. Yes. Since the degrees are the same, we default to the numbers in front of the x squareds, which is 2 over 1, which is 2. Does this graph have vertical asymptotes? It has one of them at x. Perfecto. Very good. Let's talk. Oh, by the way, why don't we cancel some stuff out and let's make a post reduction, a better function. So let's get rid of our x minus 4s because we're going to want that information later, but let's make a better function. His actual identity, if you will, is 2 times x minus 1 over x minus 3. That's the function that we should be using for our calculations, like what we're about to do. So for the x-intercept, what do we do? Make the top equal 0, and there's only one number that can make that happen, and it's 1. So the x-intercept will be at 1, 0. How do we find a y-intercept? Make all the x's equal 0. And if you do that, I agree. And if you're lost, you just need to speak. I know sometimes people are apprehensive to do that, but this should be a comfortable place for you. So if you put 0 where these little red arrows are going to point, 0 minus 1 is -1. 2 times -1 is -2. And then on the bottom, 0 minus 3 is -3. And so the y-intercept is at 0, 2/3. Is there a hole? There is. So we're really kind of just exhausting all of the possible information that we can before we get down to the graphing. There is a hole. What's the x-coordinate of the hole? It is +4. Because that. And then how do we find the y value of the hole? Plug it into your post-reduction, right? Remember, don't go back to OG or it ain't going to work. It's going to give you something over 0, 0 over 0. So if we put 4 into the improved function, the one with the purple circle around it, what's that? 4, 3, 6 over 1, 6. Glorious. So that's why this is why we did the Delta Math assignment first, was so that those aren't conversations that are vexing by this point, right? So let's get to it. Grab your ruler. Let's graph some asymptotes. So I'm going to start with my vertical asymptote at x equals 3. I'm going to make my horizontal asymptote at y equals 2. And because we don't have multiple vertical asymptotes, we've just got the standard 4 region sort of graph here. There's not that awkward sort of center part. And if you wanted to, just so you don't forget, you could also go right to the point 4, 6 and make a hole. So you go right 4 and then up to 6 and just make a little, uh-oh, got the wrong tool. Make a little hole right there. Just so you don't forget. I forget drawing holes all the time. Try not to, but I do. So we could even graph our x-intercept. There's one right here. And we could even graph our y-intercept. I mean, would I be mistaken if I said that we already kind of know what the graph looks like? The whole thing. I don't think I would be mistaken. I feel like I'm well within my rights to make some assumptions about this graph. I feel like this graph on this side looks like this. Would you agree?
For there to be a hole, there has to be the graph right there.
Yes. Yep. That hole's not going to just come out of nowhere. Like the graph wouldn't exist elsewhere, and then the hole would just suddenly poof appear somewhere else. For reasons that I don't know if I'm capable of explaining, but that just won't do. But again, let's take the safe route. And I mean, you can do like 30 seconds worth of like 6th or 7th grade arithmetic to validate or verify that it works. So let's take the number 5. 5 should be interesting to us. And we're expecting it to be, the answer to it to be somewhere in that red circle, right? If the graph is the way we think it is, let's just verify and make sure that it is. Because I would be like uber surprised if the graph just magically appears down on the bottom, but let's verify. So if you take 5 and put it in the post-reduction, 5 minus 1 is 4, 2 times 4 is 8, and then on the bottom, 5 minus 3 is 2, and 8 over 2 is 4. So that means an input of 5 is an output of 4, and that falls predictably smack dab right where we think the graph ought to be. And just really drives home the point that, yeah, we knew a lot about this graph. Just from the information that Delta Math told us to practice, and it's all that holes and asymptotes and intercept stuff comes in really handy. So now I can go ahead and sketch the graph. So it's going to come down here like this. It's going to hit that hole and just jump a little bit. And it's going to shoot through, and then it's going to asymptotically come down like this. Good so far? Get it?
Are we gonna be graded on how well we draw these lines?
Well, I mean, have you seen me?
Well,
Well, listen, as always, like here are the things I would take points off for. Are you ready? I'll just be very honest with you. If your graph goes like that, you're going to lose a point. The graph is not going to approach a vertical asymptote and then just bounce off of it back in the other direction. Like, can we agree to that? The graph is all right. I mean, the graph is also not going to come down to a horizontal asymptote and then curve upwards. Another thing I might take a point off for, what I'm trying to say is it's the whole glass house throw stones thing. Like, as you've seen, I'm not the world's best artist, right? You get that? So you might also lose points if your graph goes like that. Can we agree? Am I answering your question? Like if
well,
it's,
as long as we're in the boundaries and touching points, we should be fine.
I think so. And as long as it just generally adheres to the rules that we're talking about, like that asymptotic sort of behavior. Is it hard to draw? It is. But I'm not going to hold you like to account for perfection, but I think we can avoid making it look like this abomination on the board.
So no cool X drawings, like 3DS things.
Well, yeah, that would be appreciated. Yes, thank you.
Super.
Number 3. Super. Super. Yeah, is it super? Let's factor the top. What do we do? You pull out negative 3x, and what does that leave behind? X plus 1. Good. Bottom?
X plus 1 is minus 1. No.
It's x plus 2, x minus 1. Although this is an interesting little fellow we've got here. There's absolutely no cancellation at all. Nothing. So this will be interesting. So let's begin with our horizontal. Is there a horizontal asymptote?
Yeah.
Where?
8.
Good job. Negative 3. So remember the degrees were the same, x to the 2 over x to the 2. We defer to the numbers in front. Negative 3 over 1 is negative 3. Is there a vertical asymptote? There are 2 of them. There are 2 things that can make the bottom equal 0, neither of which has an opportunity to be removed, eliminated. So what are my 2 vertical asymptotes? Awesome job. Okay, remember vertical asymptotes come from where the bottom equals 0 if it can't be canceled. How about an x-intercept?
-1.
Yes, there are 2 of them. There are 2 numbers that can make the top of the fraction equal 0. There's -1 and there's also 0, right? So remember that for anything that's equaling 0, you have more than one opportunity, then you've got to take them both. So the 2 things that can make the top equal 0 are 0. So there's an x-intercept at 0, 0. And there's another x-intercept at -1, 0. We always know that the x-intercepts are something comma 0 because, like, for God's sake, if you're on the x-axis, your y-coordinate is 0. How do we find a y-intercept? If you make x into 0. So y-intercept is at 0 comma something.
I think zero again, right? You get a zero on the top.
You do. Yep. And we actually probably, I'm not going to say that. No, that's good. If you put 0 in the function, you get 0 on the top. -3 times 0 is 0 times whatever is still 0, and 0 divided by whatever is still 0. So it turns out this graph actually goes through 0, 0. Once. It just serves two purposes. It's weird. Not surprising. Weird. I don't even know why. It's obvious. Got a little weird guy here. What'd you say?
No.
Yeah, no holes. Because nothing had a chance to cancel. So again, you will be amazed at how much more success you have if you structurally get building. So let's get to it. Oh, I think my program might be about to crash. Oh, nope, it's came back to life. Yay.
Does it do that often?
Nope. But it's really annoying when it does, especially while I'm making a recording, because then everything gets all mookied up. So after building the skeletal structure of the graph, never a bad idea to go and plot some points. And we've got 2 points that we can utilize here. Looks like 3, but one of them is repetitive. So I can put a point at 0, 0. And I can put another point at -1, 0. I think we can safely rule out the center looking either like this or like this, right? Like that would just be impossible for it to possibly hit the x-axis twice like that. So we know that it's going to be parabolic, sort of either in a down, back, up through, or up and back down through. Bless you. You're welcome. So let's get to it. Let's start with our regions. Let's start with the region that is to the east of the, I don't know why I always work this way. I'm normally a left to right guy, but I just, whatever. So let's head over here. What's a logical X to pick for there? 2 is wonderful. So let's pick 2 and go put it in place of all the X's. I got -4.5. But that could very well be wrong. Anyone struggling with how we're getting those? Just changing X's into whatever. That's the thing about functions. You feed it whatever you want. And then you just got to let it math. It'll spit you back out an answer. So that means that we have a point at right 2, down 4.5. And remember that do not use the asymptotes as like an origin. You need to respect that 2 -4.5 starts from the origin 0, 0. So we're going to go right 2 and then down 1, 2, 3, 4.5, and we're going to place a point right there. And I feel like that's enough information for that corner, right? We should trust the process enough by now to know that that's enough. If you wanted to do more, go ahead. You can do 3, 4, 5, whatever you want. Just give you kind of something more to connect. But we're not going for perfection. We're just making sketches. Oh God. Oh God, that one got away from me. That's an ugly graph right there. That might be one of my worst ones to date. Let's tackle the other easy one, the left-hand side. Probably kind of already think we know maybe where it's going to be, but let's verify. What's the closest number to the left of the last most asymptote? -3. And use your calculator as liberally as you wish when you type this stuff in. Did I just get the same dang answer again?
I got negative.
So -4.5 again. Huh, neat. That's pretty cool. So there's a little symmetry action going on here. So if we go left to -1, 2, 3, and go down again to -4.5, we have another point. And we can again connect some dots here, so to speak. Well, that one went way better than the last one. He's looking at his homie on the right, like, I don't know what ugly stick smacked you over there, bro. Still good? Now it's time to decode the middle. Oh, Nelly. In order to do this, we just need more information. And the only way to get that information is to plug numbers in. So we don't need much, but we need something. So where do you guys want to find a third point in the center? Say it again. -0.5 is a great choice. So if we pick -1/2, then we're essentially going just right smack in the middle. And we're assuming that that point is either going to be like up here someplace or down here someplace, right? That'll tell us sort of what we need to know. So let's do it. And again, I don't know if I want to do this one in my head, but it's a little scary. So -0.5. Oh yeah, I don't want it. I don't want any part of this. I'm gonna let you guys calculate that. I'm scared. Do you want me to type it in too, or are you guys calculator abled? Cooper, are you doing it by hand? Yeah. Bold. Got -1/3. Awesome. Huge, because now we have cracked the code. And if we know, I'm going to zoom in just a little bit on the center portion. I'm going to grab this point and move it into my workspace. So when I zoom in, I don't lose it. As I go into the center a little bit tighter, that means that there is a point that is left 1/2 and down 1/3, which is right about here. And that does it. That tells us everything we need to know. Can we know what kind of structure it has to have? We know what kind of structure it very specifically can't have. But that point now tells us that the graph will go parabolically like this. You know, we only got through 3 problems today, but I would say that the sampling was very nice. So we'll pick this up tomorrow. I doubt we'll do all of them together because boy, did that feel like it dragged on, and you don't want that. So bring that back with you tomorrow. Don't worry about doing any of it or anything like that. We'll resume tomorrow.